Hello, everyone. So we were doing section 23.5 last time in class, and so that's where we're leaving off. We went to a lot of effort to show this equation right here and why that works and how we developed the maximum EMF that you're going to get from a situation. So let's go to a nice drawing. Okay, here we go. Okay, so we have this type of a situation. It's a generator, okay? And we could have n number of loops going around this loop in the middle between the north and the south poles of permanent magnets. Those guys are spinning around. There's a B field that goes across from the north to the south of those permanent magnets, and they spin around. The loop spins around, and as it does, these brushes on the rings will generate current, and we came up with our maximum EMF, or what the book calls E naught, which is terrible because it's not the initial, it's the maximum. So they should just say maximum, but whatever. So we've got our maximum EMF going from the peak and then goes down to the valley. And anytime a curve starts out at zero on the axis, the x-axis or the t-axis, then it's a sine wave. If it starts out at the maximum and works its way down from there, then it's a cosine wave. So we're starting out at zero, we're going up, we come down, and we do our sinusoidal wave like that. Okay, so that's the generator that generates, and we've got our number of circles, of loops. We've got the area for each loop, and then we've got the B field because of the magnets, the permanent magnets on either side. And then there's some angular velocity or frequency, angular frequency that's happening, okay? And that angular frequency also is what drives our sinusoidal action. So if we were going to write this total equation out, let me see if I have room. I think I can do it. So we're going to write our EMF is equal to the number of loops times the area of the loops, or average area, times the B field, times our angular velocity. And believe it or not, when you multiply all those things together, you get volts, okay? Because EMF is in volts. So all those units, they make a volt, okay? Don't even think about it. Okay, so, and then we multiply that by the sine of omega t. Okay, so that's the real equation, and all we've done here is this equation and this equation go together in there. Okay, I think you get it. So let's get back to what we were doing. So we've got omega equals 2 pi times our frequency, all right? Which means if frequency is equal to 1 over the period of the cycle, which we see down here at the bottom, that's 1 period for the cycle, and it is. So then omega is equal to 2 pi over the period. In fact, what that does for us is that means that the sine of omega t is really the sine of 2, let's do better than that. 2 pi little t over big T. Okay? So this T is really, the period is kind of like what we used to have with the tau being our RC constant. Well, this is a similar thing. This is the period. This is the constant for our the time with it takes one cycle to happen in our generator. Okay, so let's move up just a little bit. We've got this Emax and Emin, or I said Emax, negative Emax, but it is definitely negative Emax. It's also the very minimum that you can have, so that's true. The frequency is 60 hertz in the United States for a generator. You can go through and figure out what that is. What does that mean for a period of rotation? So we can just say that our period is equal to 1 over the frequency. So if we say 1 over 60, that's going to give us, I'm going to plug it into my old trusty 1.66 times 10 to the minus 2. 1.67 times 10 to the minus 2 seconds. Okay, so that's how long it takes to do one cycle in the United States. Okay, 1.67 times 10 to the minus 2 seconds. So not very long. All right. So here's the thing. And I alluded to this in class, but I wasn't able to do a very good drawing of it. So I'm going to just say now that we're going to do the thing that I kind of talked about in class. And we're going to call it a split ring. Okay? So a split ring produces only positive EMF. Okay, so we can drive something with simply positive EMF if we put, and it's nice, it's just a straight up mechanical action. So instead of me drawing, let's go to this. So here we have brushes on the rings, okay, and each one is going to generate a current in that direction, and that's going to light up our bulb. And that bulb, this situation right here is an alternating current, okay? So our voltage goes up, our current goes up. Our voltage goes to the other side, flips the current, and the current goes in the other direction. Okay, so this is an AC situation. So what we want to do is create a DC situation. So what do? We do a split ring commutator. And I don't know if you can see where the ring is split, but right there next to the arrow, you see a little gap. Okay, that gap means that the brushes will only touch the side that is bringing down current or bringing up current from the other side. So since that's the case, and then something kinetic, some water wheel or whatever is spinning this omega around so that the axis turns, that axis turning generates the current that will light up our light bulb, or we can store the current or whatever we're doing. So those are the brushes, and that is what we call a split ring commutator. Okay, split ring commutator on the test for sure. So what does that do? Every single time we drop down to 0, well, it stays down at 0 actually for a little bit. It's not perfect, but it stays down at 0 for a second, and then it pops back up because everything has shifted to the other direction. And it keeps the current always going in the same direction and our EMF always in the same direction. So it just kind of bounces back and forth. So the old split ring commutator. So I don't need to, the book does a really good job with it. I'll try and draw a little a version of it right here. And then we have a brush. I'm gonna give up trying to draw eyelashes on the brush. Imagine that that's a circle. And we'll put the other brush here. And we can stick an ammeter in there, and we can read the current. So all the rest of the apparatus is up here, all the loops and all those things. And then we'll have current. On one side, the current always goes up on one side and always comes down on the other. So when this thing gets spun around, the wires, everything gets spun around. The brushes don't, okay? So everything on this side of the brushes, everything here doesn't spin, okay? The inside gets spun because of the water wheel or car tire or whatever it is, spins. And then the current always comes down one side on the left and goes up on the right. And that means that the current only flows one direction, and we end up with that nice EMF versus time, where it does this kind of thing. And of course, there's a little bit of lag in there, right? Just because of life and friction and all that stuff. And the gap, right? There's a gap in between right there. So that gap gives us a little bit of a lag, but we're still at the tops of these is still at epsilon max. All right, our maximum EMF. I do want to mention one other thing, and that is the period is now this big. So the original period, all we've done is we've taken, so here's the first one. The second one was upside down before, and now we flipped it to the other side. The third and then the fourth. So the third would be up, the fourth would have been down, and we're just flipping it. So by the time we get here, we have seen 2 periods. Okay. So I think we should do an example, just so that we don't lose sight too much. Let's say we have a magnetic field that is 15 times 10 to the minus 3. I'm sorry. I'm looking at the wrong numbers. We have a magnetic field. Let's try this again. 1.25 Teslas. That's better. A quarter of our period is equal to 15 times 10 to the minus 3 seconds. We've got an n, so the number of loops is 200. We've got an area for our loop, and that is equal to 7.85 times 10 to the minus 3 meters squared. So our question is, what is epsilon max? So let's figure that out. It's got to be not too hard. Epsilon max is equal to n a b times omega. So what's the hard part here? We've got n. We can easily plug that in. A is quick and easy. B is quick and easy. The only trouble is omega. So what's omega? That's 2 pi divided by t. So let's put in what t is. And we're going to say 6.283 is 2 pi. And t is equal to 60 times 10 to the minus 3 seconds. That gives us radians per second. So that's nice. And that is omega equal to 104.7 radians per second. So we've got everything we need to just knock it out. So we've got our 200, and we're going to multiply 7.85 times 10 to the minus 3 times our 1.25 magnetic field times our omega at 104.7. 104.7, that's my favorite radio station. Okay. Not worrying about units. We're just going to slap volts on there because we know we've done it correctly. And so then we have EMF max of 206. Okay. So what now is our EMF average? So we've got the max. What is our average? We know EMF max has to be greater than the average. And it turns out that it's the root mean squared, right? Okay. All right, I don't know if you guys remember, but in class we did, stay still. In class, we did an example, and we used the exact same stuff, okay? However, we didn't have the split ring commutator on, okay? So our wave looked like this. And we wanted to know our EMF, and the EMF was equal to our minus N times our minus BA over delta T. And delta T is that same 15 times 10 to the minus 3 seconds. Okay? So we've got the same B. So our B is still the 1.25 Teslas. And we've still got the same area, and that was 7.85 times 10 to the minus 3 meters squared. And look at all this junk I'm collecting. And then our N, of course, was the 200. So when we did that, we ended up with our EMF is equal to, this cancels with this, we plug all those numbers in, and it ends up being 131 volts. This 150 or 131 volts is our EMF average. Okay, and if we take that EMF average and that doesn't work. Okay, that didn't work. That's fine. That's our EMF average. All right. So 131 volts. So we're comparing our EMF average with this EMF max. And of course, that comparison leads us to our max has to be always greater than the average. Okay? And that's where the average came from, what we just did. All right, so let's get back to our continuing fun. We are now going to jump to our next section, and that is back EMF. So it's called back EMF, and we're going to talk about it here in a second. So this is section 23.6. So electric motors and generators are the same thing, right? We've talked about it. It's the same thing, except for one runs forward and one runs in reverse. All right, a motor takes electrical potential energy, if you want to think of it, or battery stored energy, electrical energy, and it turns it into mechanical energy, converts it into mechanical energy. All right, so that's what a motor does. A generator takes it and goes in reverse. And we just talked about a generator. So it's going to take the mechanical energy and convert it to an electrical energy. And it's nice. All you have to do is have some permanent magnets around and you can do it. All right. So, motor and a generator, same device. One's run forward, one's run in reverse. So let's look at a motor. And I think I'm going to come down here and select that. I don't need advertisement at this point. Huh. Well, this is why I do what I do, because you'd look at that and you'd be like, what? Oh, that means nothing to me. So we're going to look at a motor. Okay. I thought they'd have more something going on there. First, current is run through the coils due to supplied voltage from an energy source. Okay, so I guess we could go back to whatever happens. Don't remember where we were. So here's our thing. Instead of us turning this crank, on the other side, we are supplying on the top end an EMF. Let's say we hooked up a battery instead of a current meter. So we take the current meter out, we stick a battery in there, and we apply a voltage to this thing, and then it will move that crank instead of our hand having to move the crank. In fact, you better pull your hand out of there. That's all I'm saying. Okay, so that is where our energy is coming from. So we're running it completely just in reverse. All right. So then, the battery is our energy source. So that's first. Second, the coil in the motor, which changes the magnetic flux, if we were going to use the same one that we've been doing, our coil has 200 windings or loops. It changes the magnetic flux, okay, as it turns. So they turn, and the flux changes. Because of that flux changing, it generates an EMF. Okay, this is just Faraday's law of induction. So, let me write down Faraday's. an induced EMF from our system. So the motor, even though it's doing its thing, it's taking source of energy of a battery and it's turning the crank. It's also working with the magnetic field that exists, and that induces yet another EMF. And we know Lenz's law, right? So there's Lenz's law. And that EMF, this induced EMF, says, I should say first, it says that the EMF induced opposes the voltage from the battery. That was turning the, what do you want to call it, a wheel or spinning? We could call it spinning the turning. I like turning. Turning the hand crank around. In the first place, so that induced EMF is going to oppose our battery's drive to turn that thing around in the first place. Oh my gosh. But it's secondary. It's smaller. It's not big. It's just a little thing. Takes us back just a little bit. And we call it this induced EMF from a motor is called a back EMF. So that's the 4 steps to get your back EMF. All right. First, you have a motor / generator. Second, instead of taking electric energy from it, you're supplying electrical energy to it as an energy source. You have some number of turns. It doesn't matter. They're all looped around inside a permanent magnet, and it's spinning. So you have this change. You have a change in your flux because of the spinning, and that change generates another EMF that opposes, because of Lenz's law, opposes our EMF that the battery is sending through. That's opposed, and that EMF, since it's opposing the original V battery, then we call it a back EMF. So we end up with back EMF. All right, that's how that works. All right, so it's essentially like saying here we have a battery. We're going to put a little switch in there. And then over here, we have another battery. And then we have the load. Oh, that looks terrible. What a terrible resistor that was. Let's see if I can do this better. Do a nice Charlie Brown t-shirt. Okay, that's our load. This is our V battery. And over here is our EMFB. All right, we're going to put a little B on there for back EMF. Okay. If the omega of the motor spins too fast, I think this is worth putting a little, we'll make a sentence out of it. If that motor if, let's say, the omega of the motor spins too fast, then VB is less than our EMF back. So the omega has to stay small, or else we're going to get an omega spinning too fast. And if it goes too fast, then that V battery is overwhelmed, and the EMF, so follow this current. Omega is small. Omega equals small. Okay, so we've got small omega. Small omega, our current is going to go this direction. All right? Because this EMF back is less than the VB. Okay, small omega. But over here we've got omega is big or fast. Big/fast. It's going gangbusters. Well, then all of a sudden, the back EMF, I just did a number on my load resistor, becomes greater. Okay, so when it's greater, we have this situation, and our current then will start to flow in that direction. Charging up the battery. Okay, so I think we should end now, and then I'm going to come back in a second, and we're going to do 23.7 transformers.